Hello everyone. Let's start a new chapter. So today I'm going to start chapter 15, and here you will be learning about laws of thermodynamics. Okay. So the first one is the first law of thermodynamics. So this law tells about the conservation of energy when heat. Okay. So here Q is the heat. Um, and delta U is the change in internal energy, and work are involved. Okay, earlier in chapter 14 you learn about another form of conservation of energy when you are learning about the calorimetry, and that time it was just this. Okay, you learn in chapter 14 you learn about a conservation of energy, and that was something like this. Okay, that means the sum of the heat exchanged in a closed system is equal to 0. Okay, and in this equation the only form of energy is involved is the heat energy. Okay, but now when we are learning about the first law of thermodynamics, then you see that heat, internal energy, and um, work are involved. Okay. All right. Now, what is the first law of thermodynamics? And it says that when heat Q is added to a closed system, okay, some of this added energy, some of this added heat remains within the system, changing its internal energy, okay, by an amount delta U, and the remainder leaves the system as the system does some work W against its surrounding. Okay, so that means Q, the heat added to the system, is equal to delta U, the change in the internal energy of the system, and the work done by the system. So W here is the work by the system. Okay, now in some textbook you see that the first law is written something like this: the change in internal energy is equal to the heat minus the work done. Okay, now before I talk more about this, let's see how it works in a simulation. Okay, so let me go to the simulation. Okay, in this simulation we can use this one. Okay, so here you see that we can add gas by using this piston. Okay, okay, so let me add some gas. Okay, so so I added some gas. Okay, now I want to show that when you add heat, so here you see that at the bottom we have a heater. By using that you can add heat or you can cool down it. Okay, so you have both options, heating or cooling. Okay, now here I cannot show directly the internal energy, the change in internal energy. But I can show that the temperature of the system changes. Okay, remember that in last chapter you learned about the internal energy for a monoatomic gas and diatomic gas. Okay, and you see that for monoatomic gas the internal energy was something like this: U 3/2 nRT, and for diatomic gas it was 5/2 nRT. So what I mean is internal energy is proportional to the absolute temperature T. Okay, so if you can show that temperature is changing, you can show that the internal energy is also changing. So although I cannot show directly that internal energy changing, but here at the top you see that it's written 300K. 300K means 300 Kelvin. Okay, so when you add heat to the system, you will see that this temperature will change. Okay, and that tells us that the internal energy is also change. Okay, and then you will see at some point when there is a lot of energy, you will see that the system here, the system is the gas, work on this container. Okay, so let's see. So I'm adding heat and you see that the temperature is increasing. Temperature increasing means internal energy is also increasing. That means internal energy changing. Okay. And at some point you will see that the lead, I mean the system does work on the lead. Okay, so here the work is done by the system. Okay, so you see that you add heat to a system. Okay, the system changes its internal energy because of this heat, and then it also work on the surrounding. So here the surrounding is the lead. Okay. All right, so you see that how first law of thermodynamics works for a simple system. Okay. Now, in the last chapter, we see that Q is positive when heat enters the system, and Q is negative when heat leaves the system. Okay. Now, for work done, we have also positive and negative sign. Okay. So if the work is done by the system, so in this example, in this simulation, the work was done by the system. Okay. So when the work is done by the system, then W is positive, and when work is done on the system, then work is negative. So remember this convention. So here I summarize uh, the signs for Q and W, and a similar sign you can have, similar convention you can have for the internal energy. So you can show that when heat enters the system, okay, then the internal energy of the system increases. Okay, when heat leaves the system, internal energy decreases. And at the same, similarly, you can show that when work is done on the system, then internal energy increases, and when work is done by the system, then internal energy decreases. Okay, so by using these signs for Q and W, and applying this in this equation, you can show that how internal energy increases or decreases. Okay, so yeah, of course we will be doing some numerical problem that will probably help you much better than these. Okay. All right, the next thing I'm going to talk about some thermodynamic processes. Okay, so there are 4 thermodynamic processes we are going to we are going to learn. The first one is isothermal process, and then adiabatic process, and then isobaric, and then isovolumetric processes. Okay, so these 4 processes you are going to learn today. Okay, so what is the isothermal process? Isothermal process is one where the temperature does not change. Okay, so T is equal to 0. Okay, now so if T is equal to 0, any heat flow into or out of the system must occur slowly enough to maintain the thermal equilibrium. So thermal equilibrium means no change in temperature. I mean, delta T is equal to 0, right? There is no change in temperature. T is the same. T is the same means delta T is equal to 0. Okay. So when in isothermal process, okay, any heat flow into or out of the system must occur very slowly. Okay. Now, isothermal curve, the PV curve is basically this one you already see in the last chapter. Okay, so this is the Boyle's law, right? You know that when T is constant, P is inversely proportional to V, right? So this is basically the same thing. So when you draw a line, this kind of line, one line is for one temperature. So for example, this line is for higher temperature. I mean, in all point of this line, the first line, higher T, the temperature is the same. That means there is no change in temperature. Okay, in the lower line, okay, the temperature is lower than the this one. Okay, but remember that in isothermal process, temperature is same, no change in temperature. Okay, all right, now what happen if we keep temperature constant? Okay, so if we keep the temperature constant, delta T, equal to 0, when delta T is equal to 0, delta U is also equal to 0, right? Why? Because you know that U is proportional to T, right? In one of the equation I wrote in the last slide, also in the last chapter, you see that U is proportional to absolute temperature. So delta U means delta T. I mean, delta U is proportional to delta T. If delta U is equal to 0, I mean, if delta T is equal to 0, delta U is also equal to 0, right? So when there is no change in temperature, and when the temperature is the same, then the first law becomes this: delta U equal to Q minus W. So because this is equal to 0, Q minus W, so Q is equal to W. So in this case, all the heat that enters the system is I mean, it converts it to the work done. Okay, so Q is equal to the work done. Okay, so if let's say a Q is slowly entering this system, so here the system is the ideal gas. Okay, this gas will do work on this uh, uh, yeah, this gas will do some and does some work on this surrounding. Okay, so here the surrounding is the piston. Okay, so what will happen is, because of this added heat in this system, the volume of the ideal gas will increase. Okay, so you can explain also this by using this PV graph. Let's say at point A, heat Q enters the system. Okay, so when heat Q enters the system, you see that by the first law of thermodynamics, all the heat will be I mean, will basically work on the surrounding. So you add Q here, and then this ideal gas will work on this surrounding. Here is the movable piston. So when the gas does some work on the piston, you see that the volume increases. Okay, so you see that as it is going in this direction, the volume is increasing. Okay, and volume increase means pressure decreasing. Okay, so so that's how the isothermal process can be explained. Also, we can see the same thing in this simulation. Okay, so here you can uh, show several processes, but I want to show you basically the isothermal process. Okay, so so you see here the left hand side, we have a arrow. This arrow tells you that heat is entering the system. So when heat is entering the system, okay, so you will see that this piston goes down. Piston goes down means the gas inside is working on the piston. Okay, so all the heat is basically converting into the work. Okay, so we can show that here, and you will see there is no change in temperature in the first graph. First and second graph, you will see that there is no change in temperature, but you will see that the volume is increasing, but pressure is decreasing. Okay, so here you see that. So you see that no change in temperature, volume increasing, pressure decreasing. Okay. All right, so that is the isothermal process. Let me go back. Okay. All right, so yeah, so this equation you already see. So for the isothermal process, this is the equation: W is equal to Q, or Q equal to W. Okay, now the next thing is the adiabatic process. For adiabatic process, Q equal to 0. That means no heat flow into or out of the system. Okay, so adiabatic means Q equal to 0, and don't confuse heat and temperature. Okay, so in isothermal process, temperature is constant, Temperature constant means delta U equal to 0. And in adiabatic process, Q equal to 0. That means no heat flow into and out of the system. So then the first law of thermodynamics becomes, so because delta U equal to Q minus W, when Q equal to 0, delta U equal to negative W. Okay, so for adiabatic process, the first law of thermodynamics is delta U equal to negative W. Now, how you can keep the heat flow constant? Okay, so you can prevent heat flow either by surrounding the system with thermally insulating material. Okay, so that is the easiest way to do this. Okay, or you can you can do the process very quickly. Okay, so that there is no enough time for any appreciable heat flow. Okay, so two way you can keep Q equal to 0. Okay, either you can use insulating materials around, or you can do the process so quickly so that there is not enough time for any heat flow. Okay, now in a PV diagram, so this is isothermal process, so where the temperature is constant. Okay, so how about the adiabatic process? Because adiabatic expansion means temperature decrease. Okay, how? So you can show that yeah, so I'm going to show you in the next slide. Okay, so adiabatic expansion, remember that when adiabatic expansion, I mean adiabatic expansion means adiabatic expansion. Okay, expansion means volume increases. Okay, now when the volume of a system increases, okay, you will see the temperature of the system decreases. So you can see this here. I think actually we don't have adiabatic here, so I cannot show you. Okay, so yeah, adiabatic expansion means volume increases, and volume increases means T decreases. Okay, T, okay, so volume increases means T decreases, and adiabatic compression means opposite. Compression means V decreases, so T increases. Okay, so when volume, when work is done, when you can go back to the first slide. Okay, so using this table and this table, you can show that when volume increases, okay, the internal energy decreases, so that means the temperature decreases. Okay, and vice versa. So I'm going to show how work done and volume are related in the next slide. Okay, and that probably help you to understand better what I mean, why in adiabatic expansion the temperature decreases, and in adiabatic compression why temperature increases. Okay, so I mean so here in the equation is something like this. Okay, now it's not clear from this equation how W is related to V, right? So now it's probably a little bit confusing, but in the next slide I'm going to show how work done is related to V, the volume. Okay, and that time you will see that why in adiabatic expansion temperature is decreasing, and in adiabatic compression why temperature is increasing. Okay, the last two process, isobaric and isovolumetric process, is very simple. In isobaric process, P is constant. Okay, and in isovolumetric process, volume is constant. Okay, so isovolumetric process also called sometime isochoric. Okay, so if in some numerical problem, if you see isochoric, it means the volume is constant, and isobaric means P is constant. Okay, so P is constant means none of the quantity Q, delta U, or W are zero. Okay, so for isobaric process, the equation, okay, the first law equation is basically the same thing. Okay, but for an isovolumetric process, okay, when V is constant, V constant means delta V equal to 0, and delta V equal to 0 means W equal to 0. Okay, I'm going to show it now why W equal to 0 and delta V equal to 0. Okay, so then the first law of thermodynamics becomes just this. Okay, and in PV diagram, so this is the isobaric process. So you see the P is constant, and this is isovolumetric process where volume is constant. Okay. All right. Now here in this slide, I'm going to show how W and delta V are related. Okay. So delta V and W related by this equation. So I'm going to show you how. Okay. Okay. To understand this, you need to know that P is pressure. Okay, so this P is pressure. Okay, and pressure is related to force by this equation. Pressure P is equal to force per unit area, or force equal to P times A. Okay, pressure, force is equal to pressure times area. Okay, now let's say we have a system, okay, a gas. So here we have the gas, and let's say a force is applied to this piston. Okay, so because of this force, I want to know what is the work done. So because of this force, let's say its initial position was this one, and then because of this force, it went to this position. Okay, so it changes by this amount. So this is the displacement because of this force. Okay, now remember that work done, the definition of work done was this: Fd cosine theta. Okay, here force and displacement both are in the same direction, so theta is equal to 0 degree, and cosine 0 degree is equal to 1, so W equal to Fd, and F is equal to PA, so then we can write W, the work done, is equal to PAD. Now AD, here A is the cross-sectional area, okay, and D is the displacement. Okay, so here you can see that the initially the volume is this, okay, and the final volume is this. Okay, now A and D, the product of AD basically talks about this amount of volume. Okay, and this is basically the change in volume. Okay, so that's why we can write W equal to P times delta V, the change in volume. Okay, so sometimes the first law of thermodynamics can be written something like this: delta U equal to Q minus delta V. Okay, all right. Now yeah, now in the adiabatic process, I told you that W I mean, in adiabatic process, delta U is equal to minus W, right? And now you see that delta U is equal to minus P delta V. Okay, now expansion means delta V is positive, right? So when a system expands, delta V is positive, right? So that means because delta V is positive, the right hand side is negative. Okay, so negative. So negative delta U means decrease in the temperature, a decrease in the internal energy, and also, yeah, also the temperature. Okay, and that's why when adiabatic expansion happen, the temperature of the system decrease. On the other hand, when compression happen, compression means delta V is negative. So negative and negative, it becomes positive. Okay, so delta U positive means internal energy increases. When internal energy increases, delta T, delta T also increases. Sorry, T also increases. Okay, and that's why the temperature of the adiabatic compression increases. Okay, so that's how. All right. Now, sometime you will be given the PV diagram. Okay, and the interesting thing is, if you can determine the area under the graph, area under the PV diagram, you can determine the work done. Okay, for example, for isobaric process, the PV diagram is this one. Okay, so uh, so the area under this graph is this rectangle, this shaded rectangle, and you can see that the work done by this shaded area is P times delta V. So another way to explain the work done is equal to P delta V is this graph. Okay, so remember that in some numerical problem, you will see to you will be asked to calculate the work done from the PV diagram. Okay, so remember that the area under the PV diagram is the work done. Okay, so for this kind of simple graph is very simple. It's just a rectangle. Okay, sometime you probably see something like this. Okay, then it is a trapezoid. If you have some graph something like this, then the area under this graph is this whole thing, and you know this is a trapezoid. Okay, all right, or you can break it into two. So one is this triangle and another is this rectangle. Okay, so you will see some problem. Now this one, the right one, is a little bit complicated, right? Because this is not a simple graph. Okay, I mean, triangle or rectangle is easy to determine. The area of a triangle or rectangle or a trapezoid is easy, but when we have a curve, it's difficult to determine the area under the graph. Okay, so even it is difficult to determine exactly, but we can approximately do that by dividing this curve into small area. Okay, and then determine the area of those small rectangles. So for example, here we break this. Okay, and then determine the area of each small rectangle and then add them together. Okay, so this way we don't get the exact value, but it's very close to the exact value. Okay, so another way to do this is by doing integration. Okay, I mean by using calculus, but here I'm not going to use calculus. So if you have a curve something like this in the second graph, okay, what you have to do, you have to break it into small rectangle and then determine the area of those small rectangles and then add them together. Okay, that's how we get um, the the area under a curve. Okay, and area under a simple graph, simple straight line, something like this, is either a rectangle or a triangle or a trapezoid. Okay, that time it's easy to determine. Okay, now let me show you all these four processes here in this simulation. Okay, so the first one is the isobaric. Isobaric means pressure is constant, right? So you see that the area under this graph is this yellow, okay, a rectangle. And here you see in the first law of thermodynamics, we have all the contribution Q, delta U, and W, okay? All right. Now, another simple process is the isobaric process, okay? So you see that isovolumetric process, or isochoric process. Isochoric process means delta V is equal to, V is constant. That means delta V is equal to 0. When delta V is equal to 0, you see that there is no graph, no area under this graph. No area under this graph means delta V is equal to 0. That means there is no work done. And here in this bar graph, you see that we have Q, we have delta U, but there is no color for W. Okay, so that means W equal to 0. So here in the right hand side, you can see that. Okay, so let me do it for expansion. Okay. Okay, so you see again that W equal to 0, Q equal to delta U. Okay, so here you see that heat is entering to the system, and the system is doing work. Sorry, system actually I mean, the internal energy of the system increases because of the heat, added heat, and there is no work done here for isovolumetric or isochoric process. Okay. Then isothermal process is this one. Okay. So where the temperature is constant, when temperature is constant, delta U equal to 0. So here, that's why you see that there is no contribution in delta U. So we have Q and W. Okay, and isovolumetric process is similar. Okay, so this is isovolumetric. So in isovolumetric process, Q equal to 0. Okay, and in isothermal and isovolumetric process, I mean, it is difficult to determine the area under the graph. Okay, so if we have isovolumetric, or sorry, isothermal or adiabatic process, then we have to break the graph into small rectangle and then add them together to get the work done. Okay, but for isochoric process, it's easy, it's basically 0. And for isobaric process, where P is constant, it's easy, it's basically a rectangle. Okay, and there are many other processes which is combination of these 4 processes. Okay, that time, if you want to know what is the work done, then if it is just a straight line, then the area under the straight line will be the work done. Okay, all right, so I'm going to stop here. In the next class, I'm going to talk about the second law. But before I stop, I want to show you this one. Okay, so here this table shows the summary of all the processes that you just learned. And the last thing I want to briefly mention is you can apply the first law of thermodynamics in a human body. Okay. So the first law of thermodynamics is delta U. Delta U is equal to Q minus W. So when you work, okay, when you do work, that means work is done by the system. Okay, heat also leaves from our body, right? When we do some work, right, that means work is done by the system. That means this is positive, and then Q is negative, right? When heat leaves the system, I mean, when heat leaves from our body, that means heat is leaving the system. Okay, so that time Q is negative. Okay, so Q is negative, W is positive. So because we have a negative sign, so when we do some work, normally this right hand side is negative. Okay, and negative means I mean, change in internal energy. Negative means the internal energy of the system decreases. Okay, and it's bad for the human body, right? We don't want to decrease the internal energy of our body. Okay, we want, in fact, we don't want also to increase. So we want to keep delta U constant. Okay. Okay. Okay, it's little bit increasing or little bit decreasing is okay, but we do not want too much decrease or too much increase of the delta U. Okay, so I mean, on an average, we want delta U to be constant. Okay, so now when you do work, because heat leaves the system, this side is negative, and though this we don't want. Okay, and to keep it constant, we have to eat food, or the stored fat basically helps. Okay, so we need energy to we need energy in the form of food, or the stored fat can help. Okay, so here you see that this lady is biking, okay, in order to keep delta U constant, she is having some drink. Okay, now when we deal with human body, so one thing you probably this phrase you will see, the metabolic rate. Now let me talk a little bit about the metabolic rate, and it is the rate at which the internal energy is transformed in the body. Okay, and this table shows the the metabolic rate for different activities for a 65-kilogram human. It's different for different person, but for a 65-kilogram human is basically these numbers. For example, when a 65-kilogram person sleep, that person needs about 70 joule of energy per second. Okay, so sleeping means we are not resting. Okay, still we need 70 joule of energy per second. Okay, when you just sitting upright, okay, you need 115 joule per second. Okay, so you see that just sitting means does not mean that we don't need energy. Okay, so we need energy. Even when you sleep, you need energy, and it's a huge amount, 70 joule per second. Okay, and when you run, you see that you need this much. When you bike, you need this much. Okay, and so on. So in some problem, we'll be using this table. Okay, I mean in a numerical problem. All right, so I'm going to stop here. In the next class, I'm going to talk the second law of thermodynamics. Okay, all right.